Welcome back to the Deep Dive, where we take the hardest-hitting research papers and distill the absolute most important knowledge for you. Today, we are deep diving into one of the core challenges driving the future of AI. It's this fundamental trade-off between having the most powerful models in the world and, well, maintaining genuine scientific openness and auditability.
It's the central tension in the field right now, isn't it? You've got these closed proprietary giants. I mean, the models that deliver incredible power, but they're total black boxes. They give researchers no way to look inside. And if we can't audit or reproduce results, we can't really call it science.
Exactly. And that lack of transparency, that's the real bottleneck for the entire community. If I can't look at the data set, I can't check for contamination, if I can't see the exact training recipe, I can't study scaling laws effectively. We need to turn AI from, proprietary magic back into auditable engineering. Before we jump into the solution offered in these sources, we need to clarify two terms. They are absolutely crucial for you to understand because they get confused all the time.
Oh, absolutely. The distinction between open weight and fully open models is, well, it's everything here. When most people hear open source AI, they often think of open weight models, like the popular Llama 3.2 3B or Qwen 2.5 3B. These models release the trained parameters, the model weights themselves, so you can download it and run it.
So you get the actual machine.
You get the final product, yes. But here's the massive limitation. The training data mix, the exact pre-processing scripts, the optimization methods, all those crucial ingredients are often proprietary or just undisclosed. It's like getting the most delicious cake, but the recipe is locked in a vault.
And the gold standard, which is the focus of our deep dive today, is the fully open model.
Correct. A fully open model provides total transparency. It releases the model weights, plus the complete training pipeline, the data recipes, the scripts, the optimization details, the full evaluation protocols. This is the only way to get genuine reproducibility and transparent auditing. It turns that black box into a completely visible mechanism.
And that's what brings us to Instella, a new family of fully open 3 billion parameter language models from AMD, powered by their Instinct MI300X GPUs. And Instella is making a big, bold claim right out of the gate. It's really the heart of our mission today.
The claim is this: Instella achieves state-of-the-art results among fully open models, and it's competitive with leading open-weight models of a similar size. This suggests that their commitment to transparency didn't force a performance compromise.
But here's the truly compelling part, the efficiency nugget that has to stick with you. Instella manages this high-level performance despite being trained on substantially fewer pre-training tokens than a lot of its contemporaries. It suggests they found a way to squeeze way more knowledge out of every single training step. It's optimization over brute force.
So if they aren't just relying on raw data scale, they must be relying on some really sophisticated engineering. Let's unpack that efficiency claim, starting with the base model's foundation, Instella 3B.
Okay, let's unpack this. So, Instella 3B is a text-only autoregressive transformer. Pretty standard architecture. 3 billion parameters. It uses 36 decoder layers and adopts the ULMO tokenizer. But the stability choices they made, that seems key to its efficiency. They didn't just use the defaults.
That's right. When you are training a massive model, stability is your first concern. Instability just causes you to waste tokens, energy, time, everything. So they deployed two specific normalization strategies to ensure stability and rapid convergence. First, they opted for RMS norm.
Root mean square layer normalization.
Right, over the more traditional layer norm. And RMS norm is known in the research community for offering better training stability, especially as you scale up.
And the second one is a really fascinating detail. It seems crucial for a compact model pushing performance like this. It's called QK norm. This is where they inject a layer normalization step after the query and key projections in each attention head, but before the attention scores are actually calculated.
This is a brilliant piece of engineering, and it's all about stability. The job of QK norm is to stop the attention weights from becoming, excessively large or extreme. If those weights blow up, they can cause numerical overflow, gradient instability. It basically derails the whole learning process. It's like trying to learn while walking on a sheet of ice. By stabilizing the internal query key mechanics, they make sure every single token processed results in high-quality, stable learning.
So if I were to simplify QK norm, it's kind of like putting guardrails on the model's internal processing. So it doesn't get overwhelmed or destabilized by noisy, overblown numbers during training. It just maximizes the value of every single piece of data they feed it.
Precisely. Stability enables efficiency. And that flows right into the training schedule. They didn't just dump all 4 trillion tokens in at once. They used a carefully calculated, staged pre-training process. And that's another crucial element of their success here.
So walk us through that staged process. What was the thinking behind segmenting the training like that?
It was about building a robust foundation first, and then strategically tuning the model for harder tasks. Stage 1 was the initial foundational pre-training on a massive 4.07 trillion tokens of general data. Basic coding, web text, academic knowledge. This established comprehensive language comprehension.
Then they moved to stage 2, which was significantly smaller, only 58 billion tokens, but extremely focused. This second stage targeted reasoning-heavy domains, which tells you they understand that complexity requires specific, high-quality exposure, not just endless repetition of general web text.
And this is where the engineering innovation for open science really shines. The synthetic data detail. Included in that 58 billion tokens were 28.5 million tokens from an in-house synthetic mathematical dataset. They didn't just scrape publicly available math problems.
So how exactly did they generate this data synthetically? I mean, while maintaining the quality needed for a transparent, fully open model.
This is clever. They took existing, verifiable math problems, specifically from the GSMA-8K benchmark, and they didn't just use the answers. They abstracted the problems into symbolic Python programs. And once abstracted, they could parameterize those programs, changing the numbers, the variables, the specific wording, to generate entirely new, diverse, yet guaranteed correct variants.
That is brilliant. It's like manufacturing high-quality, difficult, and most importantly, auditable data at the source. The beauty of this is that because the data is guaranteed correct and fully disclosed, researchers using Instella don't have to worry about the data contamination that secretly plagues proprietary models. It makes the science cleaner, right?
Absolutely. It ensures that when Instella excels at math, it's because it learned the underlying logic, not because it saw the answer key during training. And they had one final clever technique for maximizing the knowledge captured in stage 2, weight ensembling.
Weight ensembling. Explain that simply for us.
Instead of running stage 2 once and just hoping for the best, they ran it 3 separate times using different random seeds. Then they merged the resulting weights into the final Instella 3B checkpoint. Think of it like averaging the work of 3 very smart students on the same final project. The result is more robust and generally higher quality. This technique alone boosted the average performance by 5.3% relative to stage 1.
So what's the payoff for all of this specialized engineering? The QK norm, the stage training, the synthetic data? When they tested Instella 3B against the field, what did the numbers say?
First, among its peers, Instella 3B outperformed all previous fully open models by an average of 8.1%. That's a huge win for transparency. But the real headline is the comparison to the bigger open-weight competition.
Right, that's the claim that needs scrutiny. I mean, Llama and Quinn models, they often have vast proprietary data backing their foundational models. So how did Instella's smaller token count truly stand up? Did the sources indicate any areas where Instella showed a genuine weakness?
That's a fair challenge. The overall analysis shows a remarkable outcome. Instella 3B outperformed Llama 3.23b by 4.1% on average across 11 benchmarks. And while specific domain performance varied, the average advantage went to Instella. And if you look specifically at reasoning, that staged, reasoning-focused pre-training pipeline paid off big time. Instella 3B achieved a huge 29.7% lead over Llama 3.23b on the GSM-8K mathematical reasoning benchmark.
Wow, a nearly 30% lead on complex math problems in a 3 billion parameter model. That just confirms the strategy. High-quality data engineering is currently winning against raw data dumping.
It absolutely does.
Okay, so they built a strong, efficient base model. But a base model is just a predictive machine. It needs to learn how to follow instructions to be useful to you, the end user. So how did they take that robust Instella 3B and turn it into the highly capable Instella 3B Instruct variant?
That requires the post-training pipeline. That's what focuses on alignment, which transforms the model from a general predictor of the next word into a helpful assistant. This happened in 2 key steps.
Step 1. Supervised fine-tuning, or SFT. This is basically teaching the model the language of instruction, right?
Exactly. SFT involved training the model on 2.3 million high-quality instruction response pairs across diverse areas, math, coding, and general dialogue. This is where the model learns the required tone, the formatting, the ability to handle complex instructions. If you want the model to sound helpful and structured, this is where that training happens.
And step 2, the critical alignment step using direct preference optimization, or DPO.
DPO is the refinement step that enforces human values. They use 0.76 billion preference tokens to align the model's outputs not just for correctness, but for human preferences regarding helpfulness, safety, and factuality. You're essentially teaching the model to choose the better answer when faced with multiple options based on an explicit preference signal.
The result is the fully aligned Instella 3B Instruct model. And when we look at the performance of this final Instruct version, the efficiency gains, they carry right through to real-world usefulness.
It holds a commanding lead, a 14.37% average lead over the next best fully open instruction-tuned model. But what's crucial here is that the Instella 3B Instruct performs on par with, or even slightly surpasses, leading open-weight instruction models like Llama 3.2 3B Instruct and Quinn 2.5 3B Instruct. And this is on benchmarks focused on nuanced thinking, like Truthful QA, GPQA, and ICEVAL. The consistent efficiency is undeniable.
Okay, this next section is where the research gets really ambitious. The A&D team realized they had a unique opportunity here. They took their robust, efficient 3B-based model and created two highly specialized, fully open variants. Let's start with Instella Long, which is aimed at context length, the 128K context leader.
The goal here was pure application. Create a small, fully open model that can handle extremely long sequences, up to 128,000 tokens. Think processing an entire book or a stack of legal documents for analysis.
How do you even do that? How do you achieve that massive context window expansion from the original 4K limit without breaking the model? It's like taking a small car and stretching the wheelbase dramatically.
It requires systematic, multi-stage continued pre-training, heavily leveraging what are called ROPE scaling laws. ROPE stands for rotary position embedding, and it's a specific mathematical way the model tracks position. By gradually increasing the context length, ramping it up from 4K to 64K, and then training with data up to 256K context, they systematically teach the model to attend to information that is much further back. That gradual ramping is what maintains stability.
But once the model can handle a long context, you still need long context instruction data for the SFT stage, and that data is notoriously scarce. People don't often type 100,000-word instruction prompts.
Exactly. This is another area where data innovation saved them. They couldn't rely on existing benchmarks. So they synthetically generated high-quality long-context instruction and QA pairs there directly from massive documents, like ArcSIF papers and books.
So they taught the model to understand long context by using a teacher model to generate instructions based on those long documents.
That's the key innovation. They used a much larger, high-performing model, Quinn 2.514b Instruct 1M, as the teacher. They fed the large documents to the teacher model, and it generated the complex, long-form questions and answers that the smaller Instella Long model then used for its fine-tuning. It's a very efficient way to transfer complex contextual knowledge.
And the results were strong. Instella Long was highly competitive on the specialized helmet benchmark, even outperforming several prominent open-weight models.
And here's where we get a fascinating scientific insight. The sources noted that when optimizing for long context, they saw performance drops on some short context benchmarks. That's a known trade-off. But they also reported a significant drop in their toxygen score, which measures toxicity avoidance.
That's a fascinating positive side effect. Unexpected ethical benefits from purely technical optimization. Why do you think optimizing for long contexts would inadvertently reduce toxicity?
It suggests that the process of being trained and fine-tuned on broader, complex, long-form documents, things like high-quality academic papers and books, provide an unexpected alignment benefit. It might dilute the influence of noisy, toxic short-form data. The toxygen score dropped from 57.02 to 42.34, which is a meaningful reduction. It's a great example of how transparency lets us study these unintended positive consequences.
Okay, now let's turn to Instella Math, the model built purely for reasoning and logic. How do you take a compact 3 billion parameter model and push it toward complex multi-step math and strategic thinking?
This involved the most complex post-training pipeline of all, multi-stage reinforcement learning, or RL. After two initial SFT stages, one for math coverage, one for long chain of thought training, they applied three sequential stages of group relative policy optimization, or GRPO.
3 separate RL stages using completely open data sets. That's intense. Can you define GRPO in this context?
GRPO is their specialized reinforcement learning mechanism. It's designed to maximize learning from positive and negative examples in structured tasks, like mathematical derivations. And the progressive stages were key. They started with simple rollouts and gradually increased the complexity and the context length, moving from 8K to 16K. It all culminated with training on Olympiad-level problems from high-quality open data sets.
So they were systematically teaching the model not just the facts of math, but the ability to perform long, structured, proof-like derivations. What was the measurable impact of adding those three GRPO stages?
The impact was huge for such a small model. The reinforcement learning provided strong, quantifiable gains, resulting in a 10.81-point improvement over its SFT variant. That's the difference between being merely functional and being truly capable of reasoning.
And if we connect this to the bigger picture of general intelligence, there was one surprising fact about Instellamat's final performance, one that really highlights the effectiveness of this deep specialized training.
It's truly a paradigm-shifting result. Instella Math achieved the highest reported performance among all evaluated models on the Strategic Reasoning Benchmark TTT bench. And this was despite having zero exposure to TTT bench or any similar strategic gaming data during training.
Wait a minute. They trained this model intensely on mathematical and logical proof structures, but it hadn't seen any strategic game data, yet it aced a strategic reasoning benchmark.
Exactly. This suggests that the intense multi-stage RL training focused on complex, structured mathematical logic, which requires compositional thinking generalized extremely well to other forms of complex strategic reasoning. It's not just learning math facts, it's learning the structure of solving problems, which is portable across domains. That's a powerful insight into the potential of specialized, efficient small models.
What's fascinating here is how the Instella project fundamentally challenges that established narrative that performance requires secrecy and, brute force scale.
Instella demonstrates definitively that superior performance and complete openness are not mutually exclusive, even in compact 3B models. The core contribution is showcasing the effectiveness of highly sophisticated staged engineering, from the stability offered by QK norm to the efficiency of the synthetic math data, and that powerful multi-stage GRPO pipeline for complex reasoning.
Which means Instella offers a transparent, high-performance, and versatile alternative for the community. So why should you, the learner, care so deeply about having this fully open foundation?
Because knowledge is only valuable when it can be audited and understood. Instella provides full reproducibility. Researchers can now audit the entire pipeline, study scaling laws with guaranteed clean data, and understand precisely how specific training choices, like synthetic data or weight ensembling or the effect of QK norm, how those things affect outcomes. Instella is advancing the science of language modeling by enabling transparent benchmarking and reproducible research that was, frankly, impossible in the proprietary domain.
So what does this all mean for the future of AI development? The Instella research highlights the power of sophisticated, staged engineering over simply relying on massive brute force data scaling. Given Instella's success with techniques like synthetic data and multi-stage reinforcement learning, we have to ask, how quickly will these fully transparent, optimized small models start replacing less efficient, semi-closed systems, pushing auditable science and deep understandable knowledge to the absolute forefront of AI development?